Good, so we are continuing our series about the basics in parameterized complexity. And yes, we are going to discuss now dynamic programming and integer linear programming. So let's start with dynamic programming, and let's start with a simple warm-up example. So we are first going to talk about set cover. So in set cover, we have a universe U, and we have a family of a family F of subsets of U. And what we want to find is the minimum size of a subfamily f prime of f, such that it covers all of the elements in U. So for every element in U, we have a set in our family f prime that contains that element. Okay, so this is our goal. This is set cover. And the parameter that we are going to use is the number of elements in U, the number of elements in the universe. So this is our first example. Now we are going to use dynamic programming to solve it. So towards that, let us denote the sets that we have in our family F. Let us denote them by S1, S2, and so on until Sm. So M is the total number of sets that we have, and we denote them arbitrarily like this. Okay? Now we are going to use a very simple DP in order to solve it. And each entry in our DP table will be of the following form. So we have an entry MIU for every I, which is between 0 and M. Remember that we have M set, so this will correspond to that. And also for every subset of the universe. Okay? What is the meaning of such an entry? So in an entry MIU, what we want to store is the minimum size of a subfamily F prime of the sets between S1 to Si. Those are the sets that we are currently restricting our attention to. And we want to find a subfamily F prime of this family of sets, such that we will cover all of the elements in U prime. So notice that we want to cover all of these elements, but we can also have additional elements, not just the elements in U prime. Okay, but it is important that all of the elements in U prime are covered by F prime. Now, in the basis, we have when I is equal to 0, we are simply not allowed to use any set. Right? We have here S1, S2 to S0 is simply empty. So we are not allowed to use any set. So if the set of elements that we want to cover is empty, then we can cover it using 0 sets. And if this set of elements is not empty, then we just put infinity, because we cannot cover. We don't have any sets to use. Now, in our equation is also very simple. So we are looking at MIU prime, where I is larger or equal to 1, and we are asking ourselves, do we want to use the set Si, or do we not want to use the set Si? So if we are not going to use the set Si, then it means that we need to cover all of the elements in U prime using the sets S1, S2 until Si minus 1. Right? So this is the first entry here. And in the second one, we are going to use Si. So this means that we are again restricting our attention only to sets between S1 and Si minus 1. And we take Si, so we have plus 1 here. And in addition, we already covered all of the elements that Si covers, so we can remove them here from U prime. So this is a very simple example that gives us 2 to the n, we will see. But I also want to stress here that even in this simple example, it was important, the precise meaning that we gave to an entry. And that will be even more important in the next example. But even here, it is very important that when we looked at the meaning of an entry, MIU prime, we said that we need to cover all of the elements in U prime. So we need to cover all of these elements, but we did not put equality here. We only put subset equal. And this is what we need to do, because if you look at at the entry MIU prime, when we cover all of the elements U prime, and suppose we want to use the set Si in order to cover them together with other sets, then when we look at U prime minus Si, it might be that in order to cover these sets, we need to use again elements from Si, because the sets that will cover the sets in F that will cover this subuniverse, the elements in Si repeat. So we want to allow this. So it is important that here we have subset equal and not equal. Okay, it is also written here. When we allow subset equal, we can actually get smaller solutions. Is this clear? so this is a simple example of set cover. Now let's go to a more interesting example, and we will see that the meaning of the entry is very important here. I just want to mention that here the running time is 2 to the n, because let's look at how many entries we have. We have 2 to the n times m, and the computation in every entry is constant. Okay? So now let's look at a more interesting example, that of Steiner tree. So what is the Steiner tree problem? So here we are given a graph G, and we have a terminal set W, and we want to connect all of these terminals. So what does it mean that we want to connect all of these terminals using a minimum number of edges? It means that we want to find a subtree T of G, such that all of these terminals that we have, all of them will be contained in this subtree. Okay, so this should be W is V of T. Okay, so all of the terminals in W should appear in T. Is this clear? And the parameter we are going to use is the size of the terminal set that we have. So this is our parameter K. Okay, so we have a terminal set, and we want to connect all of these terminals. So we want a subtree of minimum size. Here size refers to number of edges. When I will say size, I mean subset of edges. It doesn't matter because we are talking about trees. And we want to find a subtree of minimum size that contains all of these terminals. Okay, and the size of the terminal set is the parameter. So in order to develop this dynamic programming algorithm, we need to use several assumptions. So the first assumption that we are going to use is that in our terminal set, we have at least 2 terminals. If we don't have any terminal at all, or if we have 1 terminal, then the problem is trivial. If we just have 1 terminal, then just pick that as your tree. And that's it. So now let's assume that we have at least 2 terminals. Another assumption that we want to make is that our input graph G is connected. Because suppose you have several connected components, and suppose that there is some connected component with at least 1 terminal and another different connected component with at least 1 terminal, then you can say no. How can you connect them if they are in different connected components? And otherwise, all of your terminals are in the same connected component. You don't need to use the other components, so just forget about them. So you focus on that connected component, and you have a connected graph. So we are going to assume now that the input graph is connected. So this is the second assumption. Okay, is it clear? And now, because we know that the graph is connected, in particular, we can talk about distances between every 2 vertices in the graph. It is defined. And we are going to denote it as follows. Dist uv, it means the length of the shortest path in G between U and V. Okay? Okay? Now, our third assumption is the following. Let's look at the terminal set. Then we can assume that it is an independent set. And furthermore, look at every one of the terminals. It has degree 1 in the graph. It has only 1 neighbor in the graph. We can assume that as well. Why can we assume that? So let's look at some instance of our problem. And suppose that here the red, which looks more like black here, the black vertices are our terminals. And now let's transform the graph as follows. So this is our input graph, and we want to say that this assumption is valid. So what do? We just have here some pendant vertex that we hang over every vertex that was a terminal previously. So as you see, for this terminal, now we have a different terminal that is a leaf whose neighbor is the original terminal. Now why is this okay? So suppose we have some Steiner tree here at the top. Just add these edges, and you get a Steiner tree at the bottom, right? You just add these new edges, and that's it. And in the other direction, suppose that we have a Steiner tree here. Then in order to reach these leaves, we have to go through these vertices that were terminals in the original instance, right? We have to use them. So just forget about these new edges that we added, and you get a Steiner tree in the original graph. So there is one-to-one correspondence between the Steiner trees in the original graph and the Steiner trees in the graph we've just shown. So this assumption is valid, and we are going to use it in our correctness proof. So the W is an independent set, and each vertex there is a leaf in G. It has just 1 neighbor. Okay? Yes?
Why we just do not construct edges connected?
These edges?
I mean, this edge, why we just construct it?
You say, why don't we just use this edge?
Just construct it
Anyway, our goal is to say that these vertices are leaves, and automatically it also gives us the property that they are in the dependent set. Okay? Also, when you connect to terminals, you still pay for the edge here. Okay? So now let's see our DP table. So it might not be clear now at first glance when we just look at the recursion, but it will be clear from the proof what is the intuition behind this recursion. So what is the DP table? It is of the following form. So we have here M of V and W prime for every vertex in our graph that is not a terminal, and for every subset of terminal that is not empty. So we have such an entry for every vertex, non-terminal, and for every subset of terminals. Okay? This is an entry, and what would be the meaning of such an entry? So it is like we are going to solve our problem with the terminal set being W prime union V. So in other words, we are asking ourselves what is the minimum size of a subtree T of G, such that this subtree contains all of the terminals in W prime, and in addition to that, it also contains V. Okay, so we want to connect everything in W prime and also V. It's clear? Okay. So let's see how we compute this table. So in the basis, what we have is just that the terminal set is of size 1. Then we want to have here a tree that contains W, this specific terminal, and also some other vertex V. And you want to use minimum number of edges. So we just take some shortest path between V and W. So it is the distance between V and W. That is all, when we just have two vertices that we want to connect, the terminal W and the non-terminal V. Okay? Now let's look at the recursion. So right now, at first glance, it might not be clear, but we will see from the proof that it makes a lot of sense, this recursion. So how do we compute now an entry MVW prime where the size of W prime is at least 2? We are taking the minimum over every vertex in the graph, every vertex U in the graph that is not a terminal, and we are looking at every subset of our current terminal set W prime. So we are looking at every subset which is not equal to the old W prime, okay, and also it is non-empty. And then we are going to add up the entries of MUX, MU, and the rest of the terminals, W prime minus X. Okay, and in addition to that, we also need to worry about the vertex V, right? So we also added here the distance between V and U. Okay, and soon it will be clear why it is correct. So let's look first at the easy direction. So we want to say that MVW, according to the meaning that I've just explained, right? We want a tree that contains W prime and also V, a Steiner tree of minimum size. So let's first show that it is smaller or equal than the expression we've just seen. Okay? So what exactly is this expression? So there is some U, some vertex in the graph that is not a terminal, and there is some subset of W prime. Let's call it X, which is not empty and not equal to W prime, and they realize this minimum that we got here. Okay, so the proof is by induction, the basis is correct, and now we are looking at this specific point in this specific recursion, assuming that it is correct for all the subsets smaller than whose size is smaller than W prime. Right, we're using standard induction. And what we can say from the inductive hypothesis is that if we look at this entry MUX, we are now looking at U and X that achieve the minimum. So for the entry MUX, then what we have here is a Steiner tree for X and U. Right? This is the entry MUX. What we have for the entry MU W prime minus X, we have again U, and we have W prime minus X. Okay? So the number that is writing there, the number that is written in this entry corresponds to a tree of this form. It has this number of edges. According to MU W prime X, what is writing there is the number of edges, and it has U, and it has W prime minus X. In addition to this, we also have here a path between U and V, the shortest path. So what happens when we add up all these three things together? just add the sizes, exactly what we do here. So we add this tree and this shortest path. So we have here some subgraph that contains x. It contains w minus x as well, and it also has v, right? So we have a subgraph whose size is at most, whose number of edges is at most what is written here. And it contains x, w minus x, so it means w prime entirely, as well as v. Okay, so we have such a subgraph. So in particular, there is even a subtree that contains them. Just take some spanning tree of this subgraph, and we have a tree. We have a tree with at most this number of edges, and it has w prime and it has v. So we proved this inequality. Okay? Now let's look at the other direction. So now we want to prove this direction. Okay? So let's look at the best Steiner tree that we have for w prime union v. Okay, that contains w prime and v. So it has v here somewhere. Where is the rest of the terminals in w prime? What can we say about them? So here we are going to use the assumptions that we made in the beginning. Okay? So what assumptions did we make? We said that the size of w prime is at least 1, so is it strictly more than 1. And also we know that w is an independent set of leaves. Okay. So this means that we cannot have just a tree that consists just of this terminal vertices w prime. We have this vertex v here, but in addition to this, what we know is that there will be a vertex here u, such that it is closest to v, perhaps it is v itself, and there is an edge outgoing from u to a subtree that contains some terminals, and there are also at least one other edge that is going to another subtree that contains at least one terminal, right? Because we have at least 2 terminals, and they are independent set. Right, so how can we connect them? So there must be a split here that goes to one subset of the terminals, and the rest of them will appear in different subtrees. Is this okay? We are using here the assumption that it is an independent set and there are leaves. Okay? And there are at least 2 here. And it is possible that u is equal to v. Okay? Okay. So now let's look at what we got here. So let's look at u and this set x here. So we have u and it got and there was an edge from it to some tree that contained the terminal set x, non-empty and not equal to w prime. So this is precisely what we have here, mux. So we are using here the inductive hypothesis, and we see that this part corresponds exactly to this. Okay, so mux is equal or even smaller than the number of edges we have in this part. Now what is mu w prime minus x? We are looking now at this subtree, and the number of edges that we have here, and the number that we have here is equal or even smaller than the number of edges we got here. And here we have a shortest path. Okay, so again, we are good. Okay? So what we've proved here is that when we sum up these 3 numbers, then what we get at the end is smaller or equal to what we have here. And this is precisely the intuition behind this recursive, precisely the picture that you've just seen. This is the intuition behind here. Okay? Okay, so we have also seen a more interesting example for dynamic programming. You can also notice that the running time of this example is 3 to the power of k. Because when we looked at this recursive and this recursion, they noticed that we have an entry for every subset of terminals, and we also look at every subset of that. Okay? So the total running time is 3 to the power of k, time polynomial in the input size. Okay? Good. So let's go now to the second part of the talk. And now we are going to discuss ILP. Okay. So this is the form of an ILP. So we have here, we have in this picture p variables, x1, x2, x3, up to p. And we also have here constraints. We have here m constraints. Okay? And each constraint is of the following form. So we have your coefficients for every variable, and it is at most some number here, b1. Okay? What we are asking ourselves is there an assignment of integers to these variables such that all of the constraints are satisfied? Okay, so this is the problem. Now, what is known about this problem is that it can be solved in time p to the order p times L. L is the size of the input. Notice that if you have here some number, then the size is log of that, okay, because it's the encoding of that. And it is known that this problem can be solved in this running time. So in particular, you see it's fpt in the number of variables. Our number of variables is p. And what running time did we get here? P to the order p times L. Okay? Yes?
Do we know if it's optimal or?
No, we don't know. We don't know what is the right answer here. Okay, but we have here an FPT algorithm, and now we are going to use this as a black box. Okay? So the first example that we are going to see is that of the closest string. So what do we have here as input? We have k strings, S1, S2, up to Sk, and they are over some alphabet. So let's denote this alphabet by the numbers 1 to n. Okay, so every string is over this alphabet. Each one of the strings is of length L, and in addition to that, our input also has some positive integer d. Now, what we are asking ourselves, is there a string S star of the same length length L? So is there a string S star so that it is close, it is similar to each one of the strings that we have in our input? Okay, S star is similar to S1, it is similar to S2, it is similar to each one of them. Okay? In other words, more formally, what we are looking at is the Hamming distance. So we want to find a string S star such that the Hamming distance, the number of entries where S star and Si are different, they have different characters, so we want that to be at most d for each one of our strings Si. Okay, so look at the distance between Hamming distance between S star and Si. That is at most d. Okay? So this is our problem. So we can also think about it in the following picture, like we have a matrix where every row corresponds to one of our strings, S1, S2, Sk, and here we have here L columns according to the length of the strings, and we want to find here a string S star. So I look how many times I have here a character different from S1. Here if there is some character different from S1, or if here there is a character different from S1, how many times does it occur? It should be at most d. Okay, so this is exactly what we want to fill up here, the question marks. Okay? Okay. So the first observation is that we can assume that our alphabet is actually small. It has only the numbers 1 to k. Why does that make sense? What is the intuition here? So we have only k strings. Now when I want to choose a character here, for example, for column 1, do I care that here it is right in 3, here it is right in 6, here it is right in 8? If I put here 3, then I know that it is the same as S1 and not the same as S2 to Sk. If I put here 6, then it is the same as S2, but not the same as S1 or Sk. If I put, for example, in this entry 5 here, if I put 5 over here, then it is the same as S1, Sk, and it is not the same as S2. This is all I care about. If I put a character there, who also has this character? Which string also has this character? So this is all we care about. So we can ensure that the characters here in this column will just be between 1 and k. Suppose there are some letters here, just take the first letter, call it 1. Take the second letter, call it 2. Take the third letter, call it 3. Doesn't matter. Okay? This is clear? So we can assume that our alphabet is actually 1 to k. So this is the first thing. Now we also need to define column types. So what is the type of a column? Simply look at the vector that we get here. Look at the strings S1 to Sk. When we have this representation, we have some vector. This is precisely the type of the column, the vector that we have right in there. How many types do we have? So we just say that our alphabet has size just k. Right, so we have k possibilities for the first string, k possibilities for the second string, k possibility for the last string. We have k strings. So how many types? How many different vectors can we have here? K to the k. So this is our number of types. Now this is another notation that we will need now for ILP. We will soon see. So let's look how many columns do we have of type T. Okay, so we're thinking about types now. For simplicity, let's think about types as numbers between 1 and k to the k. So how many columns do we have in our inputs that are of type T? This we will denote by nt. Okay? So what kind of variables are we going to use? So we have a variable xta for every type T and every letter A. Okay? So we have k to the k times k many variables because we've just said that we have k to the k many types and we have k letters. Okay, so we have k to the k times k variables. But what is the meaning of these variables? So when I'm looking at this variable kta, then I want the meaning of this variable to be the number of occurrences of A in columns of type T in some hypothetical solution S star. So look at S star. It has some nt columns whose type is T, right? If I'm looking at some hypothetical solution S star, it has some nt columns of type T. Then in xta of them, you will see the letter A. This is the meaning. Okay? So the constraints that we are going to have is, first of all, we will demand all of these variables to be non-negative. Okay? Now the second thing is that we need to ensure that the number of times we use a column is exactly the number of times we have it available. Right? We don't use it too many times or fewer times than how many times we have it. Right? So we are looking at every type, and we have a constraint for exactly for this. We are looking at all the variables xta, okay, for a specific type. We are summing up all of the variables xta, and we want it to be exactly nt. Okay? We're looking at all the letters, so xta should be exactly the number of times we have the type T. Now we also need to remember that our problem is to find a string whose Hamming distance from every input string is at most d. So that we can also encode here. How do we do this? So let's look now at every string I, and we want to say that the Hamming distance between S star and Si is at most d. So this is precisely what we are going to encode here. So we're looking at some I for some string Si. Now let's look, what is the Hamming distance here? Let's look at all of the types that we have, and let's look here at all of the letters which actually contribute 1 to the Hamming distance. What it means, if we look at a specific type T, let's look at every letter A such that A is not the letter that Si has. When we are looking at a column of type T, let's look at the ith entry. That is precisely what Si has, and it's not A there. But here we put A. So it means we have a contribution to the Hamming distance. Okay? So this is precisely what we compute here, the Hamming distance between Si and the hypothetical solution S star. Okay? And we want it to be at most d. So this is precisely our question, and we managed to encode it using ILP. So now we just run the algorithm we saw earlier, that I told you about earlier, whose running time is p to the order p, where p is the number of variables. But we said that here we have k to the k times k variables. So it's a k to the k. Here all stars means that we have also polynomial factors here, okay, that we're hiding them. So we have k to the k times k to the power of k to the k times k, and this is exactly 2 to the k order of k. Okay, just take the k to the k up with log, and this is what you'll get. Okay? Okay, good. So this was our first example, and now let's go to another example of ILP. So our next example will be the imbalance problem. Okay? So in the imbalance problem, in order to present it, I first need to give you a few simple definitions before we say what is our problem. So suppose we have a graph G, And we have some ordering of the vertices of G. Okay, so we have some ordering pi of the vertices of G, and here are the vertices ordered from left to right, small to large. Okay? Now, if I look at a specific vertex, left according to pi of V are all of the vertices that appear to the left of V when I'm looking at this ordering. So more formally, it means that the set L pi of V contains all of and only neighbors, only the neighbors that appear to the left. So I'm looking at all of the neighbors of V, such that according to the ordering pi, they are smaller, they have position that is smaller than the position of V. So it's all of these neighbors here to the left. So here we see that these two vertices are to the left and they are neighbors of V. There is no other vertex that is neighbor to V and to the left of V. So these two vertices are L pi V here. And R pi V is the symmetrically. Now we are looking at the right, and we are looking at all of the neighbors of V that appear after it, all of the neighbors of V that appear to the right of V. Okay? So this is L pi V and this is R pi V. Good, so in this example we can see that these are the two, this is a neighbor of V to the right, these two are also neighbors of V to the right, so this is here is R pi V. Now what is the imbalance of V in this ordering? So it's the difference between how many neighbors it has to the left and how many neighbors it has to the right. Okay, the absolute value of this. So this is the imbalance of the vertex V. Okay? So you take L pi V minus the size of R pi V and you take absolute value. So in this example we have here 3 minus 2 or 2 minus 3 absolute value and we get 1. Okay? So this is the imbalance of a vertex V in the ordering. And what is the imbalance of the entire ordering? Just sum up the imbalances of the vertices. So what is the imbalance of this ordering? I take the sum. We take the sum of the imbalance of every vertex in our graph. Okay? So what is the imbalance problem asking us to do is that given a graph G, and we also have a parameter D, and we also have a number D, we ask ourselves if there is an ordering pi of the vertices of G such that the imbalance of this ordering is at most D. Okay? And now what we are going to see here to demonstrate the approach of ILP is we will use the following parameter, which is the vertex cover of G. This will be our parameter. So we can assume that we have a vertex cover X along with our input. We can also compute it if we don't have it using the algorithm we've just seen. So we have X, which is a vertex cover of G. Okay, and our parameter is the size of X. So what is the first thing that is most natural to do? And we have this parameter K where we have X at hand and we have some ordering that we want to compute. At least for this X that we have at hand and whose size is a parameter, let's guess the ordering there. Let's guess the ordering between the vertices of X. So this is exactly what we are going to do. We are just going to go over every possible ordering of the vertices in X. And then we are going to ask ourselves what is the minimum imbalance of an ordering pi that agrees with pi x. What it means agrees, we have some two vertices here in X. One is ordered before the other according to pi x. Pi has the same. If some x is ordered before y according to pi x, then by pi, x is also ordered before y. Okay, so we preserve this ordering. How many orderings do we have? Only k factorial. Okay, so from now on, we are going to focus on this problem. We are given the ordering of the vertices of the vertex cover, and we want to find an ordering that extends that, and it has a small imbalance. Okay? Good. So now let's call the vertices in X according. Let's order them according to the ordering we are just looking at. So let's order the vertices in X by U1, U2, UK from left to right. Okay? We are now looking at a specific ordering of X. So let's look at this ordering and denote the vertices of X accordingly. Okay, and notice that all of the vertices that we've not yet ordered, they are in dependent set, right? Because we have a vertex cover X. So what are all of these vertices that we've not yet ordered? They are independent set. And let's denote that independent set by I. So now we want to use, the approach that we use here is very similar to what we've just seen. Again, we are going to have a definition of types. Okay? And the definition of type now should correspond to the elements that are not yet decided, all of these elements in the independent set. What is important for this element in the independent set is their neighbors. Those are what contributes to their imbalance. So let's say that the type of a vertex in the independent set is its set of neighbors. Where are all these neighbors? All of them are in X, because X is the vertex cover. Okay? So a type of a vertex in the independent set is precisely its set of neighbors. Okay? And now, again, like we had NT previously, let us again have a similar notation, and we have now NS. These are the number of vertices in I of type S. Previously, we have the number of columns of type T. So now we have the number of vertices of type S. Okay? So now we want to start placing these vertices that we have in I. We want to place them between vertices in X. So we have this notation. We will soon see it also in a picture. But we have this notation. We say that a vertex V is at position between 0 and K if it is exactly between the vertices UP and UP plus 1. Remember that U1 until UK are the vertices of the vertex cover. Okay? So it means that I'm placing the vertex V between UP and UP plus 1. Okay, if P is equal to 0, then it just means you are before U1, and if we are equal here to K, it just means you are after the last vertex cover vertex. Okay? Okay, so we have this, and let's look at our situation in a picture. So we have an ordering of the vertices here of the vertex cover. Say we have 5. Okay, so U1, U2, U3, U4, U5, and we can think about it like we have buckets here. Okay, we have buckets where we can place the vertices of the independent set. We can place them in this position, in this position, in this position, here, here. And what is important to notice here, all of this, say we are looking at this type, or in this specific type. When we look at all of these vertices that we have here in all of these types together are an independent set. So if we decide to put some vertices in a certain bucket, it doesn't matter what is the internal order between them. Okay? So for example, let's look at some vertex UI. What do we care about when we think about the imbalance in UI? Just which vertices are before it and which vertices are after it among its neighbors. And we don't care what are the internal order of vertices that we place in this bucket or in this bucket. When we look at the vertex that we are going to place in this bucket, it only cares about which neighbors it has to the left of it and which neighbors it has to the right of it. So it just cares about the in which bucket it is. Right? Because it's independent set, all its neighbors are the UIs. So when I place a vertex here, it doesn't care what is the internal order of vertices inside a bucket. So it's really a bucket in this sense. Okay, it's really some location when we can place these vertices of the independent set. Okay, so now what kind of variables we are going to have? Again, it's similar to what we've seen in the previous example. So we have a variable XSP for every type S and for every position P. Previously we had for every type T, type of a column, and every letter. So now we have again for every type. Now a type is a subset of the vertex cover. A type, remember, a type of a vertex in the independent set, it's its neighborhood in the vertex cover. Okay, so it's some subset of X and some position P. So we have about 2 to the K, order 2 to the K times K variables. Okay, because we have 2 to the K sets and we have order K positions. And what is the meaning of this variable that we have here is the number of occurrences of the vertices of type S in position P in our hypothetical solution pi. How many times do we place vertices of type S in the bucket P? Okay, look at the vertices of type S, the vertices of the independent set whose neighborhood is S. How many times do you take such vertices and put them in the bucket P? This is precisely XSP. Okay? So what are the constraints that we are going to have? So first of all of our variables should be non-negative. Okay? Second thing is, just like previously we ensured that we used a certain type of columns, exactly the number of times that we have it. Here we also need to ensure it for the vertices. How many times did we use vertices of type S? Exactly the number of such vertices that we have. So let's look at some type S. It's a subset of X. How many times did we use this type of vertices? So we sum up our variables XSP. Okay, we look at every position and how many vertices of type S we place at that position. That should be precisely NS. Okay? Now we have here, so these are the two constraints we've just seen. And now we have here a more complicated constraint, but it's also quite intuitive. This is just encoding the request that we have about imbalance. Okay, so how do we encode the imbalance of a vertex? So first, let's think about the vertices that we have in the vertex cover. So what is the imbalance of a vertex that we have in the vertex cover? This is what I here would encode. So if we look at the vertex UI, how many neighbors does it have before it? This is precisely what is written here, the number of neighbors of UI that appear before it in our ordering, minus the number of neighbors of UI that appear after it. Okay, so this is precisely UI, number of neighbors it has before, minus number of neighbors it has after. But in addition, this vertex cover, vertex UI, has neighbors in the independent set. So how many of them are before it, minus how many of them are after it. So this is precisely what is written here. We look at all of the vertices of type S. Those are the vertices of the independent set, such that UI is contained in S, so there are neighbors of it. Okay, so we're looking at all of the vertices of type S, such that UI belongs to S. And how many vertices like this did we place before UI? This is precisely the summation that you have here. We look at all of the position P until from 0 to I minus 1 XPS. This is just all of the vertices that we place from the independent set that we place before the vertex UI. Okay, so we look at all of these positions here before UI, minus all of the vertices that are placed after it. Okay, this is exactly what we want. It's just encoding that in ILP. Okay. And notice that we have here absolute value, but this is not really a problem here, because what we actually will write instead of this is greater or equal than this, exactly what is written here without the absolute value, and greater or equal than what is written here with minus. And it will actually be equality, because as we see from the constraints that we will see next, what we will like to do is to minimize yi. So it will not be greater than that. Okay, so if we write this with plus and with minus, we have greater or equal than the absolute value, and actually it will be equality. Okay? Now we also need to worry about that in total we got imbalance that is at most D. So what do we need to look? We need to look at the imbalance of all the vertices in the vertex cover, which is exactly what we've just done. Right, we've just looked at this imbalance of every vertex in the vertex cover, so we sum that up. And we also need to worry about the imbalance of the vertices in the independent set. So what do we have for them? So let's look so now we are looking at all of the vertices of the independent set. We are going over every position and every type, and we are looking at all of the vertices. So we are looking at XSP. We have XSP vertices of type S in position P. And what is the imbalance of each one of these vertices? What is the imbalance of each vertex in the independent set that is of type S and is placed in position P? This is precisely what we need to write here, CSP. Okay, this is this number here. So the vertex in the independent set only has neighbors in the vertex cover. We took a vertex of type S and we placed it in position P. So how many vertices from the vertex cover are up to position P, before position P? This is precisely S intersection U1 to UP. These are all of the neighbors of the vertices of type S, right? This is exactly S. And all of those that appear before position P. Okay, the bucket P is between P and P plus 1. So those are all of the vertices of the vertex cover that are before the vertex here in position P of type S, and those are all of the vertices of the vertex cover that are after it and are neighbors of it. So we also managed to encode this. So we have here exactly the imbalance that we want. We looked at all of the vertices of the vertex cover as well as all of the vertices in the independent set, and we request that to be at most D. So this is precisely our problem. We managed to encode it. And now that we have encoded it, so now that we encoded it, then we can solve this problem because we had if we go back, we see that we have 2 to the k. We have order 2 to the k times k variables. So we have that the number of variables power to order of the number of variables. So we got an FPT algorithm, which is 2 to the 2 to the order k. Okay, the number of variables is exactly this, and to the power of the same. Order of the same, this is the running time of the algorithm, times polynomial. Okay, so we've seen both of this example, how we can solve both closest string and imbalance using ILP. Okay, and this is the end of this lecture. Thank you.